Chapter 2 is all about displaying data. In the first half of the chapter, we'll look at tables and graphs. And in the second part of the chapter, we'll look at how we can make some fairly simple calculations to come up with one number or maybe two numbers to describe the data. So let's first start off with frequency distributions. A frequency distribution summarizes the data by splitting it into groups. For example, consider the set of grades by percentages. 76, basically 76%, 72%, 88%, and so forth. Well, you could have a list of the grades, but it's pretty tough to look at that and come away with any interpretation of the data, or at least easily. However, if we break it into grades, A's 90 to 100, B's 80 to 89, C's 70 to 79, and then essentially count how many data values fall in each one of those categories. Now, looking at that table, we can come up with a quick and relatively easy understanding of how our data looks. We can see that we have a lot of C's, not so many A's, not so many F's, so that in general, you might interpret the data here to say that this particular class is kind of an average class. Not that easy, but not that hard either. But I can do that right away just because I have organized the data into a data table, or what we call a frequency distribution. And basically the frequency is how many times a data value fits within a particular group, and those groups we call classes. Now there is a little bit of vocabulary. We have our lower class limits. The lower class limits are the lower ends of each class. So for the A's, 90 is the lowest percentage that you can have to have an A, 80 is the lowest for the B's, 70 for the C's, 60 for the D's, and then for the F's I just put less than 60. Upper class limits are the other side. So the highest F you could have, 59, the highest D, 69, 79, 89, and 100 for the A's. The reason I put open-ended there is in some cases it might be possible to have more than 100%, say extra credit. The class boundaries are halfway between the upper class limit for one class and the lower class limit for the other. It's basically add the two numbers and divide by 2. So for instance, the 59.5 comes from adding 59 plus 60, divide by 2. 59 is the highest F, 60 is the lowest D. Add the 2, divide by 2, and you have your 59.5. 69.5, that was 69 and 70. 79.5, that was 79 added to 80, divide by 2, and so forth. The class midpoints are halfway within a class, not halfway between classes. So, for example, if I want what I see is the 64.5, the 64.5, the second data value there, was from adding 60 to 69 and then dividing by 2. Half of 9, that's the 4.5. The midpoint for the C's, 70 plus 79, and then divide by 2, 74.5. The B's, 80 plus 89, divide by 2, 84.5. Note that our class midpoints are not halfway between, say, the lower limits. So it's not halfway between 70 and 80 and halfway between 80 and 90. It only involves the boundaries of a particular class and not what's in the next class. And then we have our class width, and please note that regardless of what you look at, if you looked at the lower class boundaries, you could see 60, 70, 80, 90. They're all difference of 10. The upper class boundaries, 59, 69, 79, again, all difference by 10. If you look at the class boundaries, you'll see, again, they're all separated by 10. And here, they're all separated by 10 again. So no matter how you look at it, all separated by 10. Now, a couple of recommendations when you're creating a frequency distribution. You don't want too many classes. Here we have 5. Depending on the data set, you might want to go 7 or 8, maybe 10 total, but you probably don't want to have something that's got like 25 classes. For example, if I had split these grades up by 5s or 3s or something, too many classes makes it harder to come away with a quick interpretation of your data. And then, of course, you need to have the same class width for every class, with the exception possibly of the lowest class numerically and the highest class. So, for instance, the F here is 0 to 59. There are no grades underneath that. So, that's a pretty wide class, where all those middle ones were 60 to 69, 70 to 79, and so forth. The A's, a little bit bigger again on the top end because I could add a little bit more to it. Now, that's a frequency distribution in general, where you have it broken into groups, and then the frequency part is how many data values fit within that one group. You don't necessarily know, if all you're looking at is a frequency diagram like this, what the actual numbers are. You just know how many fit into that class. There are, however, a couple of other types of frequency distributions that we'll be using. First, we'll look at a relative frequency distribution. The relative one is where it looks very similar to the one that we have listed up there. The difference is, instead of the 4, the 10, the 16, and so forth, we put in either their percentages or the decimal equivalents to their percentages. So, for instance, in the original frequency distribution table, we had 4 A's. But we could also write that as 10%, 4 divided by 40, or we could write it as 0.1, which is the decimal equivalent to 10%. On the other hand, in the B's, we had 10 of them. We could have replaced that with a 25% because 10 out of 40 gives us 25%. The whole point of a frequency distribution is to organize the data so it's easier to make conclusions about the data. And sometimes you don't really care what the actual numbers are. You just want to know the relative positions within each group. We also have what's called a cumulative frequency distribution. In this case, instead of the designations for the different classes as we had them at the top, in other words, we had 90 to 100, 80 to 89, and so forth, what we'll do instead is use a designation like more than 89, more than 79, and so forth. And then we'll give not the frequencies that you see there, but the cumulative frequencies. In other words, we'll start off with, hey, more than 89, well, there's 4 of them. Those 4 of them, of course, are up here in the 90 to 100 group. But then when we go to more than 79, we now have to combine these two groups. And so there'll be 14 of them that are above 79. And then when we get to above 69, we're now going to be up to 30 grades that are above 69. And so this is a cumulative effect as we progress through the classes. Now, a very special frequency distribution is what's called a normal frequency distribution. And when it looks normal, you may have also heard of this called a bell-shaped curve. Basically, you have a lot of data values in the middle and not very much on the ends, on the upper or lower end of the distribution. And it is approximately a symmetric distribution. It doesn't have to be perfectly to be called a normal frequency distribution, but when it is going to be pretty close. So that, in terms of new information, pretty much takes care of section 1, at least the first part, because I've split this into 2 groups. We're just looking at the frequency distributions for this part. Okay, what we're going to do now is look at some frequency distributions and try to make some interpretations for them. So I want to start off with this one here. and I've covered up the answer. I'll take it off. But here is a data table in which you have the pulse rates per minute. And in the first column, we have the last digit. So let's say that your pulse was actually 64 beats per minute. Then it would fall into the group of 4 because it ended in 64, ends in 4. If you had, 77 beats per minute, then you would fall into the class of 7. So, first off, it says interpret each of these frequency distributions. And what some students will do, instead of an interpretation, is they'll make what I call an observation. And they'll go, hey, there are no odd last digits with data values. In other words, when you had a 1, there weren't any. When you had a 3, there weren't any. 5 and 7 and the 9. All the odd ones, there's no data values. And so somebody might say that, and I'm like, okay, you've made an observation. That's something that you can see about the data. An interpretation is then, okay, now that you've seen that, what conclusion would you draw? It's kind of like, if somebody walked into a classroom and they were all wet, but, as far as you can tell inside the classroom, you don't know what the weather is outside. If you thought, hey, it's supposed to be a sunny day, you might think, oh, did a sprinkler turn on or something? In other words, you saw that they were wet. The interpretation now, based on the fact that you knew it's supposed to be a sunny day, you might try to come up with another explanation for how they got wet. Well, here, the interpretation is that the pulse rates were measured every 30 seconds and then doubled. Or they could have been measured every 15 seconds and then multiplied by 4. However, they were not measured over an entire minute. That's really the interpretation. It was a part of a minute, and then it was multiplied by some even number, and that's why all our frequencies end up with the even numbers. So, for example, it wouldn't be for 20 seconds, because 20 would be times 3, and odd number times an odd number would still give you an odd number. So it's something like 30 seconds, 15 seconds, it could be 10 seconds, couldn't be 12, because again 12 would be into 60 seconds would be 5 times. It has to be some amount of time that would be an even number of times it went into 60 seconds. So, a way that you can make an interpretation and then by observing the data. Now, here's our second case. These are the weights in pennies, in grams, and again, what you probably notice is, hey, we have a lot of weights there at the small side, 2.4, 2.5, maybe up to 2.6 approximately. Please note there is no overlap between classes. So one ends at 2.59, the other one starts at 2.6, but we don't have anything in the middle. And again, what might be a reasonable interpretation about that? Well, the observation is there are no data values in the middle. The interpretation is, well, hey, maybe they changed the way they made the pennies. And in fact, this did happen a couple of times. Originally, pennies were totally out of copper. And then, depending on circumstances, like, say, a world war, they decided they needed copper for other things, and they replaced copper with another material. All right, last one to look at. We have IQ scores, 50 to 69. We have 24, 70 to 89. We have 228, 90 to 109. We have 490 and so forth. So, again, what might we observe? There's a lot more data in the middle and much fewer on the extremes, and this looks a lot like what you would expect a normal distribution to look like. So, a couple of examples, and again, part of the whole point of creating a frequency table, a frequency distribution, is so that you can make interpretations about it. Alright, so now we're going to take these IQ scores that we just were looking at, and we want to be able to determine what the class width, class midpoints, class boundaries of this distribution are. And I picked this one just because there's fewer classes. So first off, class width, 20. Okay, for example, if you look at, here I have 70 for the lowest, here I have 50, here I have 90, 70 minus 50, 20, 90 minus 70, 20. I could also choose the high ends, 129 minus 109, 20, 109 minus 89, 20. The class width should be the same for both, whether I looked at the upper class values or the lower class values. All right, midpoints. Here are the midpoints for what's listed in the table: 59.5, 79.5, 99.5, 119.5, 139.5. Again, notice they're all 20 apart. And where do these come from? They come from adding the lower class limit and the upper class limit. So 50 plus 69 gives me 119. Half of 119 is 59.5. 70 to 89 gives me 159. Again, half of that, 79.5, and so forth. So those are the class midpoints. And then, finally, the class boundaries. In the class boundaries, that's taking the high of one class and the low of the next class and adding the two together and then dividing by 2. So in this case, if I look at 69 to 70, that would be 69.5. Again, 69 and 70. Add the 2, divide by 2. The 89 to 90, 89.5, and so forth. Class boundaries are almost always going to be 0.5s. Midpoints, it kind of depends on just how what the width is of the particular class. All right, now what we want to do is construct relative frequency and cumulative frequency distributions from what we see here. This is just a regular frequency distribution. You have the number of occurrences of data values that fit within each one of those groups. We want to make a relative. And again, the whole idea behind relative is instead of the actual counts, we have the percentages. And the percentages can be written as percents. That first one would be 2.4%. The next one would be 22.8%. Or you can write them in decimals. And most of the time in the book, you'll find that they're written as decimals instead of percents. So these are the actual percentages. And if they look a lot like the ones above, that's because I made the total 1,000. And so those would be the actual percentages of the 1,000 data values that you had for this table. A couple of things to note here. The frequency values can be written as percentages or decimals. And decimals just mean the part divided by the whole. So in that first class, the 50 to 69 IQ scores, there were 24 of them. 24 divided by 1,000 is 0.024 or 2.4%. You can write it either way. Just don't smash the two together. In other words, don't write your answer as 0.024%. 2.4% or 0.024. And if you're like, well, where'd the 1,000 come from? If you add up all the numbers in our original frequency distribution, you get to 1,000. So that is a relative frequency distribution. Let's now look at a cumulative frequency distribution. So notice that instead of actually writing out the particular classes, I've now written it this way: more than 129, more than 109, and so forth. If I drop the table down, so when I say more than 129, it's only this one class. More than 109, it's these two classes together. More than 89, it's all three of these. That's what you're looking at, and then we have added them up. So more than 29, well, that was just the 26. More than 109 was the 26 plus the 232. And as the example that's given there, More than 89 was the 26, the 232, and the 490, and so we add up to 748. We should end up with our total cumulative frequency count by the time we're done. So there were 1,000 total, and so I ended up with 1,000. Now, there are basically two ways you can do this. I chose the more than. You can also do this as the less than. So in other words, I could have gone less than 150, less than 130, less than 110, and so forth. Basically, it just depends on what you want to emphasize. Likewise, even with these more thans, I could have started with the more than 49 on top and then worked my way down. What did I want to focus here? Well, here I'm focusing on the highest IQ scores. But I could have reversed the entire thing and then focused on how many fell into the lowest IQ scores. So you can use less than or more than. The one key is if you use more than, then you have to use the high class limits. If you use the less than, then you have to use the lower class limits. And so that is the first part of Chapter 2, Section 1.